I want to start today by talking about the absolute bedrock of our reality, literally. Gravity is the
Totally
one
agree.
force that feels completely non-negotiable, keeps your feet on the floor, keeps the Earth orbiting the sun. It's the concept we all intuitively get.
Yeah.
But what if I told you that gravity might not be a fundamental force at all?
It's a question that sounds, almost heretical in physics, doesn't it?
It really does.
We are so used to the big four. You've got electromagnetism, the strong and weak nuclear forces, and gravity. They're the pillars. But today's deep dive is going to challenge that assumption in a pretty radical way.
Right. We're looking at a theoretical manuscript that asks a very specific, very disruptive question. What if gravity is just a side effect? What if it's basically the exhaust fumes of all the other forces working together?
Hmm.
The paper is titled Reconceptualizing Gravity as an Emergent Phenomenon, and it's by Reza Khanha from the Shahid Rajeh Teacher Training University in Tehran.
And the mission of this deep dive is to really unpack his proposal. He's suggesting that gravity is an emergent phenomenon, a composite effect created by the energy of the electromagnetic, strong, and weak nuclear fields combined with mass.
Emergent. That's a
Wow.
key word here. Before we get into the heavy physics, let's make sure we nail that down.
Yeah.
It's sort of like finding out that the color green isn't a primary color,
Right.
but it's just what happens when you mix blue and yellow. Green emerges from that mixture.
Probably. Or think of wetness. A single water molecule isn't wet.
No.
Wetness is a property that only emerges when you have billions and billions of molecules interacting. Conk is suggesting gravity is the wetness of the universe. It's not a thing in itself, it's what happens when the other forces interact in a specific way.
That is a wild concept.
Yeah.
But why go down this road? I mean, Einstein seemed to have gravity pretty well figured out.
Because of the biggest headache in modern science, unification.
Yeah.
We have general relativity, which is the big, smooth physics of space and stars, and we have quantum field theory, which is the chunky, jittery physics of atoms and particles. And they hate each other. Mathematically, they just refuse to work together. This paper suggests a new way to bridge that gap by changing what gravity is.
Okay, let's unpack this. To understand the new theory, we first need to look at the status quo. How do we usually think about gravity?
Historically, we start with Newton. Gravity is a force. Earth pulls the apple. Apple pulls the earth. Simple.
Simple.
Then Einstein comes along and changes the whole game. He said gravity isn't a force, it's geometry. Matter bends space-time, and that curvature tells matter how to move.
The classic bowling ball and a trampoline analogy.
Uh-huh.
The heavy ball curves the mat, and the little marble rolls toward it.
Precisely. Now here's the nuance that usually gets glossed over, and it's critical for this paper. Einstein's equations actually say that all energy contributes to that curvature, not just mass.
All energy.
Energy is energy. E equals mc squared, right? Mass and energy are interchangeable. So theoretically, light, heat, magnetic fields, they should all cause gravity.
But wait, when we calculate the orbit of the moon, we're not factoring in the magnetic field of the Earth, are we?
No, we're not. In practice, physicists almost exclusively focus on rest mass, the heavy stuff. They treat the energy from, say, electromagnetic fields or nuclear forces as negligible. Just little side notes. They assume they're just rounding errors compared to the mass of a planet.
So we've just been ignoring the contributions of the other forces because they're usually small.
That's Kanka's core argument. He says this simplification is a huge mistake. We need to stop treating gravity as a soloist that only cares about mass. We need to see it as a choir. His whole reconceptualization is that gravity is the result of the total energy density of all fields in nature.
I like that image, a choir. So if I'm hearing this right, he's saying gravity is like a composite material, like bronze.
Yes, that's a perfect analogy.
Bronze isn't an element on the periodic table. It's a mixture of copper and tin. You mix them and bronze emerges.
That is the perfect way to put it. In this view, gravity is the bronze. The copper and tin are the other fundamental forces. Electromagnetism, the strong nuclear force, the weak nuclear force. When they exist in a space, their combined energy creates the effect we call gravity.
Okay, so if gravity's the soup, let's look at the ingredients. The paper breaks this down to 4 specific components. It decomposes the stress energy tensor, which is just fancy talk for the bucket of energy, into 4 parts. What are we dealing with here?
First, you have the mass field, T mass. This is the energy from rest mass, E equals mc squared. This is the one we all know. It's the bowling ball.
Right, the standard ingredient, but then we get into the stuff we usually ignore.
Correct. The second ingredient is the electromagnetic field, TEM. This is the energy stored in electric and magnetic fields. We're talking about photons. Light. Now, this is important. Even though a photon has no mass, it has energy. And because it has energy density, this paper argues it must contribute to gravity.
That makes sense. If Einstein says energy equals mass, then a really dense magnetic field should technically have a gravitational pull, just like a rock.
Exactly. Next, we have the heavy hitters of the subatomic world. The strong nuclear field. T-strong.
And this is what holds atoms together, right?
Yes. It's the energy from gluons that bind quarks inside protons and neutrons. And the paper describes this as having immense energy density. And immense is, it's actually an understatement here.
How immense are we talking?
Well, think about a proton. We usually think of it as a solid little particle with mass, but it's made of 3 quarks. If you add up the mass of those 3 quarks, it only accounts for about 1% of the proton's total mass.
Wait. Only 1%. Where does the other 99% come from?
It comes from the binding energy of the strong nuclear force holding those quarks together. That energy is so intense that it manifests as mass. So when you step on a scale, 99% of the number you see is actually the weight of that energy.
That blows my mind every single time I hear it. So Kaga's arguing, if this force is responsible for 99% of the mass, why wouldn't it be directly responsible for the gravity?
Exactly. It's the engine room of reality. If that's where the energy is, that's where the gravity comes from.
And a fourth one.
The weak nuclear field. D-weak. This involves W and Z bosons. These govern particle decay, like radiation. It's a shorter range interaction, but again, it involves energy. It's another ingredient in the soup.
So the core argument here is all about energy density. It doesn't matter where the energy comes from. A heavy rock, a magnet, a force inside an atom. If it has density, it creates gravity.
Precisely. The paper argues that every single interaction possesses field-specific energy. Even if particles are technically massless, like photons or gluons, they have energy density. And in this model, gravity is just the geometric response to that total density.
This feels like we're moving away from the abstract idea of bending space and getting into something more, more mechanical.
It's definitely trying to be more concrete. The paper moves away from the complex tensors of general relativity and proposes a scalar volumetric approach.
Scalar volumetric. It sounds impressive, but break that down for us.
So in general relativity, we use tensors, these complex mathematical objects. Conca is simplifying. Scalar just means a single value, a magnitude.
Okay.
And volumetric means we're looking at a volume of space. Think of it like scooping up a cubic meter of space and just summing up all the energy inside it. That sum gives you the gravity at that point.
So instead of measuring a curve, we're measuring like a pressure.
That's a great way to think about it. The total pressure of all these fields interacting is what generates the gravity. And the paper actually proposes a novel formula for this.
Okay, let's walk through that formula, but keep it simple. What does it look like?
It looks like this. G of x, that's the gravity at a specific point, equals a constant, k, multiplied by the sum of all those densities we just talked about. You've got the density of mass plus the density of the electromagnetic field, the strong field, and the weak field.
Okay, I see the list of ingredients there. Mass, EM, strong, weak. But I noticed some Greek letters attached to them. Alpha, beta, gamma.
Those are the weighting coefficients. Think of them as the tuning knobs.
The tuning knobs.
The author is suggesting that while all these energies contribute, they might not all contribute at a 1-to-1 ratio. We know mass converts to gravity efficiently, but does a magnetic field convert to gravity at the same rate? Or does the strong force couple to space-time differently?
So if you were cooking, these would be the measurements. 2 cups of mass, a tablespoon of electromagnetism, maybe a pinch of weak force.
Exactly. And honestly, this is where the theory needs the most work. The paper admits we don't know the exact values of alpha, beta, and gamma yet that need to be found experimentally, but the structure of the formula is what's so important. It implies gravity is a geometric response to the total field energy.
It really changes the picture. Gravity isn't just matter attracting matter, it's space-time reacting to the presence of field energy.
It does, and that leads us to the historical context because, interestingly, Kangha isn't the first person to suggest gravity is emergent. This isn't completely out of left field.
Oh, right. Who else has been down this road?
The paper cites a few heavyweights. Andrei Sakharov, way back in 1967, he suggested gravity acts like a macroscopic elasticity.
Yeah.
Imagine space-time is like a mattress spring. Gravity is just the stiffness of that spring.
That's a cool image. Gravity is the stiffness of space. And there was another one mentioned, Verlinde.
Yes, Eric Verlinde. He proposed that gravity is an entropic effect. It's all about thermodynamics and information. But his theory is it's very abstract.
So how is Kong Ha's theory different from those?
Kong Ha's model is energy-centric and volumetric. It's much more practical. He's not talking about abstract entropy. He's saying, look, we know the energy density of a magnetic field. We can measure it. Let's just add it up. It offers a concrete way to calculate this.
Speaking of sources, there was something in the paper that really caught my eye because you don't usually see it in physics manuscripts. The author quotes a theological text.
Yes, I noticed that too. It's a quote from Imam Bakir from the Bihar al-Anwar collection.
The quote is, "God has placed forces on the earth that hold things together, and if those forces were not there, everything would be thrown into the air."
It's fascinating that the author included this. He uses it to frame the scientific worldview. The interpretation here is that these invisible forces, the strong, weak, and electromagnetic interactions, are literally what bind matter to the Earth.
It's a bridge between a cultural perspective and the scientific one. If those nuclear forces didn't exist, atoms wouldn't hold together. Matter would just disperse. So in a very literal sense, those forces prevent everything from being thrown into there.
Right. And the paper uses that to support the idea that gravity is the result of these binding forces. If you take away the strong and weak interactions, you don't just lose atoms. According to this theory, you might lose gravity itself, because the energy density creating it would vanish.
That connects the glue of the atom to the glue of the solar system in a really poetic way.
And if we connect this to the bigger picture, the implications are actually mind-bending. The so what factor here is huge.
Let's get into that. If this theory is right, what does it change about how we see the universe?
The most fascinating implication is massless gravity.
Massless gravity. So gravity without a planet.
Exactly. If gravity comes from energy density and not just rest mass, then you don't strictly need mass to have gravity. You just need enough energy.
Can you give me a real-world example? Where would we see that?
Think about high energy zones. The paper mentions regions with intense magnetic fields, like around magnetars.
Neutron stars.
Right, with incredibly powerful magnetic fields, trillions of times stronger than Earth's, or high-energy plasmas. In these places, the mass might be low, but the field energy is off the charts.
So a cloud of super intense magnetic energy could have a gravitational pull, even if there's no rock in the middle of it.
According to this formula, yes. It would curve space-time just like a planet would. This opens up new ways to explain, exotic astrophysical structures.
Yeah.
It might even offer a solution to dark matter.
Dark matter. That's the stuff we can't see, but we know is there because of the extra gravity, right?
Exactly. We see galaxies spinning too fast and we say there must be invisible mass there. But Kong's theory flips it. Maybe there is an extra mass. Maybe there is just extra field energy that we haven't plugged into the equation. The gravity is real, but the matter is a ghost.
That would solve so many problems. What about the beginning of everything? The Big Bang.
That's the other big application. Right after the Big Bang, the universe was a hot, dense soup of energy. Not solid mass, it was a quark-gluon plasma. Traditional gravity models struggle there. This model, which relies on energy density, might actually handle the early universe much better.
It feels like this theory is trying to be the translator between two different languages.
That is the perfect way to put it. You have Einstein's general relativity, the language of smooth geometry, and you have quantum field theory, the language of chunky particles and fields, and they usually speak past each other.
And this theory says the common word they both understand is energy.
Yes, energy is the currency. By defining gravity through energy density, Kong Ha is trying to unify physics. He's taking the chunky world of gluons and bosons, calculating their energy, and using that to build the smooth world of gravitational curvature.
It's really elegant when you think about it. Instead of inventing a new particle like a graviton, he's saying, we already have all the pieces.
Yes.
We just haven't added them up correctly.
Which is often how the biggest breakthroughs happen. Not by finding a new thing, but by seeing the connection between the things we already have. Parsimony. If the strong force is already there, use it.
But I have to play devil's advocate here. If it's this elegant, why isn't this the standard model? What's the hurdle?
The hurdle is measurement. Remember those coefficients, alpha, beta, gamma. We need to know those values. We need to be able to measure gravity with such incredible precision that we can detect if a magnetic field is pulling on us. And gravity is just notoriously weak. Building a sensor sensitive enough to weigh a magnetic field is currently beyond our tech.
So it's a beautiful framework, but we need better tools to prove it.
Exactly. But it is testable. That's the key. It's not magic, it's physics. It predicts that if you concentrate enough field energy, you will see an anomaly in gravity.
Which leads me to one final thought I want to throw at you.
Uh.
A bit of a provocative question.
I'm ready?
The paper emphasizes that this is a testable model.
Right.
So if gravity is just a composite of these other energies and we're getting better and better at manipulating, say,
I
electromagnetism,
don't see where you're going with this.
could we hack it? If I build a machine that creates a super dense electromagnetic field, could I artificially engineer my own gravity? Or even anti-gravity, without needing a planet-sized mass to do it?
That is the ultimate sci-fi dream, isn't it? If gravity is just a recipe and we learn how to cook with the ingredients, then theoretically, yes, we could bake our own gravity.
Artificial gravity.
Or the reverse. If you can manipulate the fields that create the curvature, you might be able to negate them. If gravity isn't a fundamental constant of nature, but an effect of other forces, then mastering those forces gives you the keys to the castle. You wouldn't need a massive rocket to leave Earth. You'd just need to manipulate the local energy density to flatten the space-time around you.
That is a wild thought. We're obviously a long way from building a warp drive in the garage, but just the idea that gravity is something we could engineer rather than just obey, that changes the whole perspective.
It moves gravity from the realm of fate to the realm of technology. It's a dizzying thought.
I think that's the perfect place to leave it. We started by questioning the bedrock of reality, and we ended up with the blueprint for a spaceship. Thanks for listening to this deep dive into the nature of reality.
Always a pleasure to explore the universe with you.
We'll catch you on the next one. Keep looking up.